Let's talk about the generalized power rule. Given u is a function of x, so it could be a polynomial, it could be an exponent, it could be a lot of things, and we'll get to all the different things it can be. Then when I go to take the derivative of a function u to a power n, I bring down the power n, I subtract 1, now I have nu to the n minus 1, then I multiply by the derivative of whatever u is. The generalized power rule is often called the chain rule. A chain is made up of links. So I put a picture in there to make you think about it. So remember that when you use this rule. A single link is not a chain. So if you answer a single piece, term, factor, or whatever, then you didn't perform the chain rule. When you perform the chain rule, you should have multiple pieces when you take the derivative. So let's take some examples to really help see what that looks like. So let's start with this one. I have f of x is 4x cubed plus 2x squared plus 9x to the fourth. So this 4x cubed plus 2x squared plus 9x, that's my function of x, and then my power is the 4. So when I first start the generalized power rule, the chain rule, I'm going to bring that 4 down, and I'm going to change that power to a 3. See how I didn't change anything on the inside of the parentheses? It stayed exactly like it was. So I just brought down the 4, change it to a 3. Afterwards, I multiply the derivative of the inside. So 4x cubed becomes 12x squared, 2x squared becomes 4x, and 9x becomes 9. Can you see in this example why we call it the generalized power rule, the chain rule? We still bring down the power, we still subtract 1 from the exponent, but we don't take the derivative of the function until after we've changed the powers. So it still has that power rule feel, but it also has that chain feel that we have different links. We have the 4, we have this part cubed, and then we have this 12x squared plus 4x plus 9. So there's our links that make up our chain. So let's try it again. This one's a little bit smaller. Here I have 3 times x squared plus 1 to the 5th. So the first thing I'm going to do to take the derivative is bring down that 5. So 5 times 3 gives me 15. The x squared plus 1 stays the same, now it's to the power 4. And then inside x squared plus 1, derivative is 2x. I can simplify this because I have that 15 and the 2x. I could bring those two together and get 30x times x squared plus 1 to the 4th. All right, so I'm just going to keep going and give you a few more examples. So this one looks pretty similar. I threw an e in there just to show you what happens there. So this one, when I start with 7 times 4 e to the x plus 2x minus 5 cubed, first step is bring down that 3. So now I have 21. But I keep the 4 e to the x plus 2x minus 5, and now it's squared. Inside 4 e to the x, the derivative is still 4 e to the x, plus 2x becomes 2, and the minus 5 disappears. All right, let's change this up and do one we couldn't have done before we learned the chain rule, which would be the square root of 3x plus 5. And why do I say we couldn't have done it? Well, the other ones we could have done. We could have expanded them out, but I'm not really interested in multiplying something out to the 5th power, to the 7th power. But there is no way to expand out something to the square root power. So I can rewrite it as the 3x plus 5, make it the 1/2 power. Now I'm going to bring that 1/2 in front. I'll leave it as 3x plus 5. And subtracting 1, I have a negative 1/2 as my new exponent. Inside the 3x plus 5, that derivative is a 3. Looks kind of ugly, so I'm just going to rewrite it. And remembering that this negative means it goes into the denominator, I'm going to put the square root of 3x plus 5 in the bottom. 2 was already in the denominator, so I'm just going to leave that there, and this 3 is just going to go in the numerator. That looks a lot prettier. All right, this one, again, let's look at something we haven't talked about. And we did something sort of like this in a previous video where we said, how would I take the derivative of something with a constant in the numerator? And we used the quotient rule. Well, here I want to tell you that we can get around the quotient rule now that we have the chain rule, and only in particular cases. And here's a case where we can get rid of the quotient rule. Because the numerator is just this constant 1, I'm going to rewrite it as 4 ln of x plus 3x to the negative 5th power and just use the chain rule and skip the quotient rule altogether. So using the chain rule, I'm going to bring that negative 5 down. It's 4 ln of x plus 3x. When I subtract 1, it's negative 6. Be really careful with negatives. It's really easy to go, it was 5, now it's a 4. Make sure you pay attention with negatives. Negative 5 goes to negative 6. Inside 4 ln of x, well, natural log becomes 1 over x when I take the derivative, so 4 ln of x becomes 4 over x. And the derivative of 3x just gives me 3. This doesn't look too pretty, but it doesn't look too awful either, so I'm just going to leave this one alone. All right, here's a bigger one because I'm going to do two things here. I have f of x is 3x plus 5 to the 4th times 8x minus 7 to the 6th. When I hear the word times, it makes me think, oh, I'm doing the product, so I better use the product rule. And important to make yourself start thinking these things of what kind of rules am I going to use for derivatives, because there's a lot going on. So in this one, I'm going to use the product rule. And then because I have parentheses to a power, and I'm going to use the chain rule. And in most problems, you're using the power rule, but eventually you're not really even thinking about that anymore. All right, so planning this out, I think, well, let's start with the product rule. The product rule really pushes this. So the product rule starts with, well, let's take the derivative of 3x plus 5 to the 4th. So I'm taking this first term, derivative I have 4, 3x plus 5, now it's cubed, and then back inside I get a 3. The second term, 8x minus 7 to the 6th, I just write it again. Then I say plus, and I switch it. So now I write the 3x plus 5 to the 4th, and I take the derivative of 8x minus 7 to the 6th, which means I would first bring the 6 down, write 8x minus 7 to the 5th, go back inside those parentheses, take that derivative, it gives me an 8. Well, that's a lot of stuff. So let's see what we can do to make that look a little prettier. So the first thing I'm going to do is just kind of look at term by term, and I think term is separated by a plus or minus. So here I see 4 times 3. Let's make that 12. So at least I went from 2 down to 1 for my coefficient. Same thing over here. 6 times 8 is 48. Okay. After I do that, I start going, okay, well, what do they have in common? The 12 and the 48, they have 12 in common, so I'm going to factor out a 12. 3x plus 5 is in both terms, and I look at the powers 3 and 4. I can take out the smaller power, which is 3. And the 8x minus 7, again, I can take out the smaller power, so I go 6 and 5. That gives me 5. Okay, so you're always looking for what do they have in common, and then you take out as much as you can, which is usually the smallest exponent. Okay. So now I'll go back and go, okay, taking this 12 out means it's just gone now. The 3x plus 5 cubed, I took all of it out. But this 8x minus 7, I took out 5 of the powers, which will leave 1. So that's what this here is that 1 more. Okay. On the second side, this 48, I divided by 12, so I still have 4 left. The 3x plus 5, I took out 3 terms, or 3 powers, so I still have 1 power left. And then the 8x minus 7 to the 5th is completely factored outside. So I leave that alone. So you see the factors are the same. I'm going to drop these parentheses. I'm going to multiply the 4 through the 3x plus 5. It gives me 12x and 20. I can say 8x and 12x is 20x. I can say 20 minus 7 gives me plus 13. This is my form that I want. I do want you to do this. I know I put this on tests. This is going to be really important as we move forward. So practice, practice, practice this factoring. Remember, this isn't muddied up by the calculus. It's really the algebra of factoring that usually confuses students. So do plenty of these in the homework. Practice. We'll go over them in class as well, but it's really important to do these.